Session 2, the Control System Engineering. I'm the chair, my name is Alena Kozakova, and we have 4 papers scheduled for today. All of them are presented in person, and I would like to invite the first presenter of the paper by Bozhidar Rakov, Georgi, Ruzhekov about H-infinity reduced order control of a thermal plant.
Chairman, dear colleagues, I would like to show you a little bit of our joint work with our esteemed colleague, Associate Professor Georgi Ruzhekov. The general idea in this presentation will be given a plant with a simple dynamics. By simple, I mean overdamped, self-regulated plant, to try to reduce the order of the controller itself, which is based on the H-infinity norm framework. Here are the points that I would like to address in my presentation. First, the need for reduction. We know that the controllers designed using the H-infinity norm lead to high order, which is equal to the order of the plant itself plus the shaping filters. But is it always needed to use this complexity, this high order? Maybe not. If we can reduce the order of the control, there might be some benefits. For example, simplicity in case of software implementation, easier to understand, easier to debug if some problems arise. Also, might be possible to reduce the computing resources and the calculation of errors accumulated due to the limited precision of representation of numbers in computer systems. The test subject that we used is the thermal plant. Most of you are familiar with it, but for the others we have 4 aluminum pieces. For 3 of them we have a thermocouple sensor. On the last one we have a fan controller, on a fan. We did a system identification procedure and received a model in state space form from ninth order. Based on this model, we will design some controllers. The design of the controllers themselves. We are using the well-known mixed sensitivity S/KS structure with 2 arrangements of the integral part, one in series form and one in parallel form, to check if there will be some differences in the performance of the system and if this somehow will help in the reduction of the controls. We are using the shaping filters to shape our frequency responses in a way to achieve some performance. To reduce the controllers themselves, we used the MATLAB function barret, first by plotting the Hanke similar values. The function in MATLAB tries to minimize the normal and the absolute error between the highest order controller and the reduced one. Based on the bound on the absolute error for the series controller, we decided first to reduce the order from 18 to 14 and then further to 10. If we try to reduce it further under 10, simulation showed that there is a steady state error. So we decided to stop at 10 for the series controller. On the other side, for the parallel controller, again for comparison reasons, we decided to reduce to 14 and 10, but here it was possible to reduce the order even further. We were able to reduce it to the order of 3, but the system exhibited some overshoot more than 10%, so we decided to stop at 6. Some comparisons in the frequency domain, starting with the output complementary sensitivity functions. With blue color or subscript H, we are showing the highest order controller, and with red color, this is the lowest possible controller. For the series form on the left hand side, and on the right hand side we have comparison of the close to the complementary sensitivity function with the parallel controller. With the series form there is almost no difference, but we can observe some minor variance in the mid and high frequency ranges for parallel one, but mind you, this is the worst order possible. Here is 6, here is 10. Going to the output sensitivity functions, again there are no differences for the series controller, and we have some variations in the closed loop system in the parallel controller, but this is negligible difference. At the end, we have the sensitivity to input signals. Again, we have a small variations in the mid and high frequency ranges for the parallel controller. Let's talk a little bit about the implementation itself. The plant is controlled with a programmable logic controller, so we need digital implementation. The series controller is implemented in discrete state space form using these equations where E with subscript I is the integral error. These are the equations for the parallel form. We have two inputs, the error itself and its integral. Since the parameters themselves are calculated on a separate computer, we need to transfer the matrices to the controller, and we do this by use of OPC. Some problems. There are no ready available functions for matrix calculations. So we needed to write some simple function just for matrix addition and matrix multiplication, matrix addition. There is of course some anti-windup mechanism by back calculation, possibility of owing data, etc. etc. The experimental results. We conducted one set of experiments which consist of reference change on the 3 loops with different amplitudes. To emphasize the similarity between the 11 closed loop systems, I plotted all of them together. Something to note, our inability to control strictly the room temperature leads to different initial conditions in the experiments. These are results for the first output. Here we had some results for the second output, again similar transient responses, and at the end we see the results for the third output of the thermal plant. At the end we calculated some criteria like rest time, settling time overshoot, and here we have the square root of the sum of the square error, and this is square root of the sum of the control signal. Looking again on the numerical results, we could see that there is quite some similarity between the 11 control system, despite their reduced order, which supports our idea that for simple plants it is possible to reduce the order without losing too much of the performance itself. And thank you for your attention.
Thank you. So please, it's time for questions.
Congratulations, a very good practical result. I have several questions. My first question is how to use the weighting function, V.
Which function?
How to choose, how you
the weighting function. We chose it in a way to...
Oops. It's very important for the quality of the
I decided to skip this in the presentation, I'll tell you, just to find my slide.
Yeah. In the form of transfer function?
Yes, the shaping filters. First for the output sensitivity function. We chose bandwidth, desired bandwidth for the output sensitivity function, plus a maximum for the sensitivity function, and a desired error in the state. And for the control signals, we try to have at around 40 decibels in the low frequency ranges, like control signals. In the high frequency range, we decided to decrease it by 20 decibels per decade until we get to 20.
You obtain very nice result without the oscillation.
The shaping filters are missing on the... Here you mean?
The thermal plant is delay or without delay?
There is around the model that we received from the identification procedure have one sample time delay, which is 10 seconds in our case. But for this dynamics, which is around in open loop 20,000 seconds, I would say that it's not big.
My final question, the control action, the coefficient of the control action, how do you compute? Oh yes. See?
The matrices of the controller with use of the HMC function in MATLAB.
You use the robust toolbox?
Yes. We give the so-called extended plant, which consists of the plant itself to be controlled and the shaping filters. Then we do the procedure with the HCM function in MATLAB. We receive these matrices, then we transfer them to the OPC.
Thank you.
Thank you. Any other question, please?
Yes. One of the main issues in model reduction in closed loop is what to do. First, to reduce the order of the model and then design the controller, or we use the full order model, design a controller, and then reduce the order of the model. As I understand, you are applying the second approach. You have high order model, design a controller. I heard about 18
Yes, 18.
order, and then reduce.
Yes.
Okay. Have you made a comparison between these two possibilities? First, to reduce the model, then design the controller with the reduced order model, and then what you have done actually, what you have shown, use high order model, design a controller, which is also high order since H infinity, and then reduce the order of the model.
Actually, we did that, but I forgot to mention it in the presentation. Here, with letter M, 6 and 3, these are the reduced models. From ninth order, we reduce the model to 6, then to 3, and on this
Of the model?
Yes, the
Of
model
the
itself. Then
plant,
we
yes.
of the plant. Then we design controls on the reduced model.
Okay.
I have the
And
results here.
what showed the comparison? Which
For this plant, which, as I said, have a simple dynamics, almost no difference.
almost no
whatsoever.
different.
Yes, excluding the fact that we have different initial conditions. But these are all the 11 controllers,
Okay.
which include the controls designed by the reduced order models.
Okay.
Just to say this, the models themselves, maybe the 9 order is a little bit higher, but I was a little bit strict to pass the correlation tests in the identification procedure. If I tested the reduced models, they did not pass the correlation test, but despite that, here we can see that
Okay.
this
That
was
concerns
Yes.
controller design.
yes.
Okay, thank you.
Thank you. Okay, I didn't see the model of the thermal plant or what kind of thermal plant it was. Did you mention maybe?
No.
Because the next presentation also relates to this
Yes,
thermal plant. Maybe you can just formulate the problem.
The plant itself, we try to control the temperatures on the 3 of the 4 modules. We control them with electrical heater. And we try to achieve desired temperature levels on the 3 of the pieces. But the problem is that it's a multivariable.
Multivariable, yes.
Yes, so there are some interconnection between the... But the main idea here was to try to reduce the order and see if we can achieve the same kind of performance but with lower order. Actually, if you later would like to check to see the plant itself, like transfer matrices.
Yes, because state space is
Yes,
the
I can
same
show
for-
it, but unfortunately I don't have it like a slide on the presentation.
Okay. Thank you. So, if there are no more questions, I would like to thank Mr. Rakov, and please stay there and continue with the other presentation. again with the same authors, by the same authors, Mr. Bozhidar, Rakov, Georgi, Ruzhekov, and now it is about H infinity multivariable PID control of this thermal plant.
Which I'm on again, and dear colleagues, the second presentation that I will show you is about multivariable PID control. Here our idea was to check another MATLAB function called hinstruct. We wanted to try if it is possible to design a multivariable PID control and to compare it against some other algorithms. Again, the talking points of my presentation. As we said already, we use the same plot, so I'll skip it to not bore you anymore. But just want to know the following thing. Although the plant itself has simple dynamics, there is some constraint on the achievable performance based on the control signal itself. For perfect control, we would like the smallest singular value of the plant, the scale plant, to be over 1. Above the equation, I am showing you a graph of the singular value of the scale point, which shows for us that for sufficiently larger reference change or disturbance change, we will hit the saturation limit. So this will be a problem, and I will show it later. Again, with the design of the controller, we use the same mixed sensitivity S over Ks, with the difference that our controller this time has a fixed structure and a fixed order. It is a transfer matrix with elements which are transfer functions that have the equation shown here, which is discrete parallel control. About shaping filters, they are absolutely the same as in the previous presentation. Again, we want to achieve a certain bandwidth and a maximum of the sensitivity function and certain amount of control signals in the desired frequency ranges. Firstly, we designed one multivariable PID controller, but preliminary simulations in MATLAB showed deterioration of the performance when we hit the saturation limit. So we designed a second multivariable PID controller with the goal to reduce the control signals, but at the expense of slower transient responses. So we have two multivariable PID controllers. Again, some comparisons in the frequency range, starting with the complementary sensitivity functions. On the left-hand side, we have comparisons between the two PID controllers that I mentioned previously. With red color or subscript F is the first multivariable PID controller, which I will call for convenience the fast one. And with blue line and subscript S is the second multivariable PID controller, which I will call for convenience the slower one. Since we decided to check the hinstruct function against 4 other multivariable controllers designed on the norm infinity, this is a comparison between 4 other controllers and one of them multivariable PID controls, which shows that for this particular case we don't have big variations. Again, next output sensitivity functions, we could see again difference in the bandwidth of the controllers. We expect some difference in the transient responses, and this is a comparison between the 4 other norm infinity and the faster one of the 2 PID controllers. At the end of the frequency comparison, since again the control sensitivity. As I said earlier, the second PID controller is designed in a way to have lower control signals in the frequency range, as we could see from the singular values, and again small difference between the full norm infinity controller and the faster PID. What about the implementation again? As I said in the previous presentation, we control the plant itself with a programmable logical controller, so we need a digital implementation, which I'll show in a moment. Again, the parameters are calculated on a separate PC with MATLAB, then we send the parameters to the OPC connection. Again, we have anti-windup mechanism, but this time in a different structure. I'll show it in the next slide, which is this. For the implementation of the digital controllers themselves, the separate transfer functions, we use here the velocity form. Why? We would like to factorize the integral of every 3 controllers in this way, so it would be simpler to use some techniques about anti-windup. In our particular case, we use the quantic of the integral part when we hit the saturation limit. We did this time 2 sets of experiments. The first one is again reference change on the 3 different loops. And here we have with red color the full-order norm-infinity controller. And we decided to compare everything again with the blue line, so-called decoupling bit. We tuned additional controller based only on the information for the steady state, and then through auto-tune procedures designed decentralized bit control with use of the decoupling matrix. And these are some of the comparisons. As we could see, the full-order norm-infinity controller, in our case, gives the best results, but the slower multivariable bit controller with purple line and decoupling bit have some comparable performances. The outlier here is the so-called fast bit controller, which I said that have a wider bandwidth, but when we hit the saturation limit, I'm not sure here if it is a numerical problem, if the used anti-windup mechanism is the problem or the parameters themselves, but what happens here, we, for a short amount of time, we exit the saturation limit, and despite the fact that we have still a big control error, the control signals decreases, which leads to this slow dynamics and slow transient response. I forgot to mention these are results only for the first output. These are the results for the second output, similar picture we could see. And as for the third output, the second set of experiments was the following. We applied same amplitude reference change to the 3 control loops, but this time only with 15 degrees to avoid this problem of hitting the saturation limit with the fast bit controller. As we could see, these results are in line with what the frequency responses showed earlier. Actually, the so-called fast bit controller has faster reference than the slower one that we designed earlier. At the end again, we crunched some numbers and compiled 2 tables to show some comparison for rise time, settling time, overshoot, and again the square root of the sum of the square of the error and sum of the square of the control signal. The graphical results and the numerical ones show us that for this particular case, the use of this him-struct function, which I forgot to mention, solves the problem for H infinity design of the control for fixed order, fixed structure. Shows comparable performance with the full norm infinity controller, as with the, at least interesting to me, the simple decentralized split with only static decoupling matrix. Again, thank you for your attention.
I'm waiting plenty of questions.
I have one question. How was tuned the slow PID controller?
Oops. I tuned it in a way to decrease the bandwidth and to increase the weight on the control signal, so that I would have lower amount of control signal, but for the expense of smaller range of the bandwidth, so that my control will be slower, but will have smaller control signals to avoid the problems with the anti-windup. But the shaping filters are absolutely, for the first control, same as the previous presentation.
Thank you.
Next question.
My question. Is it possible to compute the controller parameters independently or by computation of the one problem? It is very difficult to compute the controller matrix transfer function of the controller independently. How do you compute this Q11, Q1A and
MATLAB has implemented the so-called tunable PID controller, which is some kind of programming object for them. In these parameters, they are tunable. I forgot to mention the presentation. This algorithm implemented in MATLAB is actually presented in an article of Icarai and No, if I'm not mistaken, in 2006. And their implementation of this numerical algorithm is implemented in MATLAB themselves. So we calculate...
matrix of controller?
Yes, my structure of the transfer matrix itself represents transfer functions, which every transfer function has this...
It is very difficult to compute this coefficient of this matrix controller.
I'm not sure about the details of the numerical implementation, but I can show you later that it works.
Ensuring the stability and the performance.
What I was able to skim through the article themselves, their first idea is to ensure internal stability of the control loop. And the second idea is to try to minimize the non-infinity itself, but always internal stability first.
You know the mathematical models of the process or that process?
Yes, it is the same...
Which order is?
9 order.
But the transfer function matrix.
For the controls themselves.
No,
the transfer functions. No, I use the Platin state space. I can give the MATLAB a state space object, but it gives me transfer functions for the control itself. How they do it, I'm not sure.
Yes, very good result. This numerical procedure is very complicated.
All credit goes to the authors of the paper itself. We just use the algorithm through MATLAB.
Next question,
I will just add how this is made. So the approach of Kamen and No is to first ensure the stability, and then they use the steepest descent. This is not optimal for the general case, but in the case of designing such a structured controllers, they show that the delimitations are not so high in strength. So there is very high possibility that you obtain the optimal controller in this case. Even if not statistically, they prove that their controller is very close to the optimal. And this is also applied 2 years ago in a mix in another function, even for mu synthesis, which is pretty new in MATLAB, but works very well for structural mu synthesis. For controllers with a given structure or at least a given order, which is practically the same.
If we're talking about optimal controller, the gamma value for the H-infinity norm was around 2. So these controls are obviously not optimal, but for this one we have kind of good performance.
Okay. Any other questions? Please.
Is it possible to simulate on the laboratory test bench a time-varying system parameter? For example, time constant, which depends on time of some of these heaters. Is it possible to...
I'm not familiar that much with MATLAB. It should be possible. We have simulation with model with fixed parameters, but maybe there is a way to vary the parameters with time somehow. But I'm not completely sure about this.
On the laboratory test bench?
The test bench itself, or just a simulation. Test bench itself with this plant, I would say that probably is not possible, but on that topic, our colleague Georgi Ruzhekov already designed a new physical plant for us, which is two tank systems, where it would be possible to change the position of the valves, where we could test these algorithms not only for nominal performance, but for robustness. If we turn the valves left and right, maybe we can check are these controls actually robust or not, since our results are only for nominal performance. But for the thermal part itself, I'm not sure that we can do it. We can change the structure, but it would not be easy to implement.
Okay, thank you.
Okay, so no more questions. If not, so thank you, and I'm pleased to award you a certificate of attendance and successful presentations.
Thank you.
Congratulations.
Okay, hello. I'm going to present a paper entitled PID Control of the Inverted Pendulum. Yes.
Let me try.
Yeah.
Computer.
You can be behind and just.
Okay, so what is inverted pendulum? It consists of two parts. A card which is moving along a line, and a pendulum which is staying on the card. It can be pointing downwards or upwards, depending on its motion. What we have as state variables are the position of the card, the displacement with respect to the coordinate system, the velocity of the card, and the angular position and angular velocity of the pendulum. Here you see the free body diagrams for the horizontal motion and for the angular motion. So the inverted pendulum system is a fourth order dynamical system, and as I mentioned, we have the position of the card, the position of angular position of the velocity, the position of the pendulum, the velocity of the card, and the angular velocity of the pendulum. Here the parameters, the system parameters, we have mass of the card, mass of the pendulum, distance from the axis of rotation of the pendulum with respect to the center of mass, the moment of inertia of the pendulum, the viscous friction coefficient in horizontal direction, the viscous friction coefficient in angular direction, the gravitational constant, and the horizontal and vertical force exerted by the card on the pendulum. These are our variables. We use to develop the dynamical system of the inverted pendulum system, the Lagrangian framework. That means we work with energies, and our main equations are the Lagrange-Euler equations, which are presented here. For computing the Lagrangian function, we need to compute the kinetic energy, which is computed like that. The first three expressions are modeling the horizontal motion, and the last expression is modeling the angular motion. As well, we need the potential energy, which is computed based on the gravitational force. Here are the equations which are developed for this framework, for the Lagrangian framework. We have the first equation is related to the horizontal motion, and the second equations are developed with respect to the rotational or angular motion. So based on these Euler-Lagrange equations, we develop the equation in state space. As you see, we have a nonlinear dynamical system. So in order to design our controllers, we used a linearization for small deviation of the pendulum in upper unstable equilibrium point. Based on this linearization, we obtain these two equations. If we consider the viscous friction coefficients to be 0, we get this equation of the pendulum, which is second order, and the corresponding Laplace transform. This is the characteristic polynomial. However, here we consider the viscous friction coefficients. The first one is with respect to the horizontal motion. The second one is with respect to the angular motion. The next part of developing the system model is to make some identification procedure, basically performing some parameters, some experiments. The parameters such as masses and lengths can be measured directly from the parts of the card pendulum system. Other parameters such as moments of inertia of the rotating parts, as well as the viscous friction coefficients, can be obtained by performing some experiments. So here is the pole of the pendulum. It consists of a load and the pole rod. These are the distances which we measure. Then we apply some mechanical relations to develop the moment of inertia with respect to axis of rotation, which is placed in the center of mass. Then we use the Steiner theorem to develop the moment of inertia with respect to the axis of rotation, which is different than center of mass. So based on this, here are the variables, the parameters actually which we measure, and based on this experiment, we obtain the moment of inertia of the pendulum to be this quantity here. In order to obtain the viscous friction coefficients, we also perform some experiments. The first experiment is with respect to the rotational motion. We set the pendulum in free motion around the axis of rotation, measuring the amplitude of deviation, angular deviation of the pendulum load with respect to the zero position. We obtain this variable, which we use later on to obtain the viscous friction coefficient with respect to rotational motion, which is given by this number here. We can also obtain the viscous friction coefficient of the horizontal motion, of the linear motion, and based on certain experiment, we obtain the viscous friction coefficient with respect to the horizontal motion to be equal to this number. Now, since the viscous friction coefficient with respect to the angular motion is relatively small number, as well as the moment of inertia with respect to the rotational motion, we can set these quantities to 0. And finally, we obtain the model of the inverted pendulum card system like this. The sign here appears negative because we use angle of rotation in clockwise direction. If we consider the angle of rotation in counterclockwise direction, we got this transfer function. This is the transfer function which we are going to use in order to develop our controller. Now, as you see, the necessary conditions for stability are not satisfied, so the system in upper position of the pendulum is unstable. So first of all, we have to stabilize. The PID controller which we use is the standard one, presented by this transfer function, and the method of tuning the parameters of the PID controller is by using the method of dominant poles placement. That means two most closely placed to the imaginary axis poles. So here are some relations concern second order systems, and we have set some values of the overshoot as well as the settling time. We obtain the dominant poles, which depends on this value. This is the damping ratio, and this is the natural frequency of the second order system, which is presented like that. And using this transfer function, we see that for a second order system, by computing the damping ratio and the natural frequency as shown before, we get this step response, which completely satisfies the performance indicators shown before. Now, the point is how to select the third pole, because this is a third order system. And based on several experiments, actually, we obtain the placement, the influence of the third pole on the system performance. So initially, we choose the third pole to be slightly to the left of the real parts of the dominant poles. We obtain this step response. The settling time is satisfied, but the percentage overshoot is too high, and is quite large actually for such kind of system. So we use several other selections like this one, and finally that one. So for the second one, we get again poor performance with respect to the percentage overshoot, but when we set 100 times to the left the third pole with respect to the dominant poles, we get this step response, which satisfies the criteria, the performance criteria set at the beginning. In conclusion, we have developed the model of the inverted pendulum, implementing, using the Lagrange framework for model development, dynamical system model development, using some identification procedure to obtain the parameters, And finally, we tune the PID controller based on the criterion of dominant pole selection, showing the influence of the third, of the placement of the third pole of this closed loop system, how it influences actually the system performance. So, thank you for your attention.
So my question is, how all this fits in the framework of the control limitations? Because this is the main problem in such setups.
What do you mean, control limitation?
For example, this pole minus 200, does the real physical setup could actually perform?
Well, that's basically you compute the parameters of the controller based on the closed loop characteristic equation. So whenever you choose the third pole at certain place, you have to equalize both sides. From one side, the closed loop characteristic polynomial based on the pole placement, and for the other side, the closed loop characteristic polynomial where every parameter member of the closed loop characteristic polynomial depends on the parameters of the PID controller. And you make the correspondence. It's a linear correspondence, basically. It's not any kind of nonlinear function or whatever.
Can you show slide 17?
You mean the...
Here.
Okay.
It's very interesting, the last graph.
Yes.
It's so much energy you have here. It's not physically correctly, I think.
What do you mean?
We have output. What is it?
Is the
Тя скача веднага, където е пунктира.
Step response output.
step response?
It's not output. The controller output in this situation.
Is the system output.
Това са 20 хода.
The left one is position and the right one is the position of pendulum.
Motor control. It's not possible to use some.
What is not possible?
There are no control signal depicted in this one.
Yes, of course, but it's short.
Short time, it's not physical.
It's not physically.
This is what I
My
did.
question is not possible.
It's not possible physically to make this jump.
Yeah.
It's with very small time constant actually. Here
I think
very
that
small.
energy, motor energy must be so high.
Motor energy to be so high. I don't think so. I mean, I'm not showing the motor energy here, but it shouldn't be so high. What do you mean, so high? Where do you see high energy here?
Do you have a picture with control signal?
Signal.
I have not shown the control signal here. This is the output.
Because according to the recommendations on pole placement, the poles should be placed as close to each other as possible. Because if
that's
one
my yes. That's what I have seen. I mean, when I see close the real parts of the system are -1, the dominant poles, and I choose -2 as the third pole.
Yeah.
And when I plotted the time response, the step response, I get about 40% overshoot.
It's a tricky
And
system.
my initial setting was less than 10%. So basically, one of the research goals here, I would say, is to show the dependence of the placement of the third pole, which is not dominant. The dominant are these two,
Yeah.
which are shown there. The placement of the third pole with respect how it influences the behavior.
And didn't you try to place it to the right of the dominant poles?
No. If
That would be
I
interesting.
well,
Because the
if
system is not minimal phase,
Hmm?
so
Yeah,
there
yeah,
should be some.
We have restriction from the right
Yeah,
zero.
Yes,
Yeah.
there are also one restriction,
Uh,
which I didn't see here.
Well, let me show you the transfer, if I have it. The transfer function, the open loop transfer function, had this expression in the numerator, which is the PAD numerator polynomial, and this expression in the denominator. So this is the open loop system. Then, based on this, cascade connection between the PID controller and the system model developed so far, I obtained the characteristic polynomial of the closed loop system, which looks like this. As you see, if I choose certain values of the PID regulator, first of all, I can make the system stable. At the third, on the second place, I move the third pole to the left. That means I don't want to, I want to keep the system stable, and I obtain several other step responses. This is the first one, this is the second one, and so on. I think I have one with -20 and so on. So what I observed is that the settling time almost it doesn't change, almost no change. The only change is with respect to the percentage overshoot. Nevertheless, the percentage overshoot decreases when I move the third pole to the left, but very slowly, with small amount. Then finally, with that value of the third pole of the system, I got this step response.
Okay, so
How the model was validated? I don't see any noises on model dynamics, random disturbances, and so on. Which is the practical keys?
Well, I didn't
Never
consider
we have the only these equations, and always we have noises, random disturbances, and so on. And the friction coefficient never known exact.
Okay, I didn't consider any noises acting on the model.
You may
This is not
as minimum.
You see, this is not a statistical procedure for model development.
Yes, of
This
course.
is a straightforward procedure based on the system dynamics and the experiments which I did in order to develop the system parameters.
But at minimum in closed loop simulation, you have to model the error as minimum, the error from ADC conversion and DAC conversion, which always
Okay. All all these experiments are simulations. Okay? There is no AD on DA.
Theoretical issue because the system per se is not so simple to control. So
With PID control, single input, single output PID control.
and
Here we have to use PID controller with 2 inputs and 1 output.
and the placement is more complicated.
1 input from pendulum position or angular velocity,
The input
and the other input
is
is
the force
for the
acting
card
on the
position.
Output.
Input for the controller, output
The
for
input
the
is the
system.
force acting on the card, and the output is the angular deviation around the upper position.
And
These are
another
the input.
output is the card position.
I
In
don't
plane.
consider it. My goal is to obtain the
The
angular deviation.
right figure was with card position, or it's slide 17.
This is the output, which is the angular deviation of the pendulum around the
Ah,
upper equilibrium point.
The left one is the angular position,
Angular deviation, yes.
angular deviation from the upper position.
Right.
Second one,
All these are, they show the difference when I select the third
now
pole
I understand.
at particular place.
You regard only the task for stabilization.
Stabilization,
In
yes,
the upward
stabilization.
position. In the upward
Not
position.
the other part is quite difficult. I didn't consider it. My goal here is to explore how the selection of the third pole will influence the performance of the whole system.
But here we have a restriction from the non-minimum phase 0 of the plant. If we choose very large module pole of closed loop system, then we obtain very large undershooting closed loop
Here is the numerator
system.
polynomial, okay,
Where?
of the PID controller.
Where we?
And this is the model of the system, which is that one. It's unstable, but I don't have 0 in the right half plane.
It's both unstable and non-minimum phase, and maybe it is not possible to.
This model should be validated on a real system.
Should be.
Okay, so let me close the discussion. You can go on during the lunch then. Thank you. Okay, so the last but not least presentation is by Alexander Hotmar, and the title is Algorithm for Predicting Daily Volatility of FOREX Markets. The floor is yours.
Thank you, colleagues. I want to present you an algorithm for predicting daily volatility of forex market. Few common words. When you want to analyze price movement of the markets, you need to, when you see one picture, first you need to have a base to understand when one move is big or not. And one of the best solutions of this problem is daily volatility prediction. What is the main problem for applying this? You can find some developers which give estimation of the daily volatility, but the main problem is missing of historical data. Today, they give you the prediction, but do not give you prediction for yesterday, what they predict yesterday. And this is not possible to estimate how accurate was this estimation. Some other developers give one estimation, but in the middle of the day change it, and no history date again. And this is useless. Maybe some people. The other problem, cost algorithm. You see the estimation, but you don't know how it is done. One more problem. The developer can change the algorithm and the accuracy of the results, and you can estimate what will be the result of this change. So this is, for me, is a big problems. I tried to create my own algorithm, and how the test was done. I use 21 currency pairs to check my algorithm, and use one year period, and this means approximately 250 predictions per currency pair. So this is a good statistical piece. What we can do, what can be the input data for the estimating the daily volatility. One of the main indicator is the day of the week. Every trader knows that the markets moves more in Wednesday and move less in Monday and Friday. So this is one of the main indicator. Another possible indicator is trend. Forex market is range market, but in some cases trends appear. If we have a trend in the market, we have big volatility, obviously. Another possible indicators, very simple, last day. Direct extrapolation. Yesterday 100 pips, today 100. You can use monthly seasonality on something, other things, but the result's not good. In my investigation, the best results I reached by first two indicators. So, how I'll calculate the estimation for each of the indicators? I use this equation and make a simple combination by the two indicators here and calculate the error. This is very simple approach, and one engineer maybe think it is possible to make better results with some more complex algorithm. My experience simply says no. In almost all cases, in Forex market, the simplest way is the best way. I try a lot of variations. This is the best. So, what is the results? On the first picture, you see in blue the accuracy of week of the day indicator. This is the error. And this is the number of the periods. So you see here the optimal values. The orange is trend indicator, and the gray is combination of the both. So you see here we have 35% error, and this value is not so big in the Forex criteria for accuracy. Another thing which I do is to make a little filtration of input data. I remove the two big values from the input. And on the second picture you see the new results. Obviously a little bit better, approximately 5%. Maybe you see by the indicator week of the day, you see here optimal values and here quasi-optimal. By indicator trend here and here, but it's not obviously, and maybe it's not true, that if you get the estimation of both indicators and their optimal days back and summarize it, we will achieve the optimal value. So I make the tests in all possible combinations. Here is week of the day and week of the day days back, and here is trend days back coefficient. In the table you see the combined estimation error, and here you see the optimal values in this corner. And for me, 29.530, this is at the limit of the possible when you use only historical data. This analysis is only for historical data, not used future events information. So, what is the conclusions? We have a few indicators to estimate, and I found two of the best. By single indicator, the accuracy is approximately 37%. By the single indicator with filtrated input data, approximately 32. And combined estimation, approximately 30%. If we want to achieve more higher accuracy, below 30% error, we need upcoming events. This is the economic calendar. We know if today have news, the volatility is higher. So, thank you.
Please.
Do you use mathematical model for prediction or not?
Excuse me?
Do you use the mathematical model for the prediction or not?
What mean mathematical model?
Or
Very
regression model. It is
When
very difficult to predict without the mathematical model.
When you estimate by historical data, more complex algorithm give a better result. A regression model, I use it when put in the calculation the news, and the result is very good. But this is not of the part of, is not part
Do you
of
use the term optimal coefficient? How do you find the optimal coefficient? Optimal, from mathematical point of view, using the criteria.
I don't remember because the last when I worked this was before 2 years maybe. But
The term optimal coefficient is strictly connected to the criteria. How to find
No, the problem is with the probability density. Usually all these models, regressions, time series on, work with Gaussian distributions. But here the distributions are not Gaussian. Sudden events can happen which will destroy all your model. If these processes were predictable, the guys who are running the models will become very rich. The point is that this destroys all the theories. And yeah, there are different approaches actually to tackle it, but it's not
this is not normal. This
model-based.
is normal here. Of course, it's possible to something happens. For example, war, and the markets start move abnormally. But the important here is to put in the model everything you can, and take the estimation, the most possible, the best estimation you can achieve. Unexpected news or something else, of course it is possible, but we can't do anything about it.
Okay. Any other question, please?
If it is a stupid question, please excuse me, but why you use this period 1 year, the third criteria, if I'm right or wrong, 2015 for 1 year?
Why exactly 2015?
Yeah, why exactly?
Very good question. Because I make a lot of investigations, and almost all of them is on this period. And I want to make I want all of my investigation be on this period to can put it together in some time. And this is the reason for this magical 215.
So it's convenient for you.
It's convenient for you. It's for traders, Wall Street. They have all these kind of models.
Okay. Yes.
Okay, my question is, I'm guessing that you're using 1 week prediction depth, right? Data. 7 days.
7 days.
Back?
Yes.
No, not exactly. For the indicator parameter, I used 15 days back, but for parameter day of the week, I get 15 weeks back, because I need the value for example, Monday last week, Monday 2 weeks last, and so on to 15.
Because from the table, this was my guess that you were using only 1 week, and this was quite insignificant. If it's using so many weeks, okay. Another thing, let's say, you can try using neural networks. Let's say in the past I've done the same with neural networks. You can get 90% accuracy, but there is always, these famous cases when you get speculants like Soros, that he destroyed the markets in 1990.
He's responsible for everything.
But the thing is, you can have this model, but the event of speculation, you have players that can externally influence the markets. And this is like you're expecting here to have nice weather, but when they make the speculate, it's like raining snow. So no model can predict that.
Yes, of course. And
About Soros, underestimate inside trading. Okay? It's forbidden by law, but if you know how to use it, you can gain.
Not only him, there are key players that can influence the market, so that's why.
of course, the mood of the markets is the response of the acts of the participants. So I don't think that the Soros is so big and so strong to move the markets extremely up and down.
In 1992, read the history, 1992 he bankrupted the British pound. So read the history.
No, he predicted. He predicted, and Bank of England says Soros is responsible. But they have a problem in their economy, in their financials, and Soros was clever enough to see it and make money from this.
So there are all smart people. Believe them. All smart and very experienced, even though they lose sometimes.
I can give you
Sometimes win, sometimes lose.
one movie, The Big Short, and this is by the real events when some smart people predict the collapse of the financial market in USA before 15 years and make a lot of money. But the problem is not in them. The problem is the bankers.
So can you predict
No.
if our national team will win or lose today against Litva?
No.
You see?
No more questions? Thank you for the fruitful discussion. The topic on control engineering. And let me award you this certificate. Thank you for your presentation.